Monday. And then I think, again, probably Tuesday we'll do like a little review, and then Thursday I'll have like a really short quiz because it's only going to be over 2 things. So shouldn't be too much going on there. But everything, these 2 things here, the solving and the graphing of rationals is very different than the next thing we're going to do. So it's good just to cut it off and move on. So I think the central question today, how do we find the domain and range of rational function? So as much as we found domain and range before, you would think that wouldn't be an essential question, but it is actually different for rational functions. So good to highlight it. I feel like my handwriting's horrible there, but too bad. How do we find the domain and range for a rational function? Essential question today. So, we've been working with rational functions over the last 2 days. We've seen that really one of the keys is that what a rational function is that it has a variable in the denominator. We saw from some of the problems that we've been working on solving that sometimes there's also variables in the numerator, but there has to be a variable in the denominator. And so, we kind of define a rational function as a function of the form that where we could have 2 other functions essentially just dividing each other to make up this one function. But sometimes a function can be as simple as like 1 is a function. F of x equals 1 is a function. But again, the denominator would have to have a variable in it. So because there's a variable in the denominator, there are variables that we could plug in, or values of x that we could plug in, that would make that denominator 0. We've been talking about how that's not okay. All right, and so if a value of x makes the denominator 0, then that value of x must be excluded from the domain, saying that we can't use that value. Okay? Because we can't divide by 0, or when we try to divide by 0, we get something that's undefined. Okay? So we have to say that those values are not allowed because they make up this number that doesn't exist. And so what happens, because we're excluding x values from the domain, we end up with is something that could be discontinuous. And so reaching way back into our little math brains, back in September, we talked about discrete functions, and we talked about continuous functions. And back then it was the discrete functions were just a bunch of dots, right? And then the continuous ones were the ones where we were connecting. And that's really trying to make sure that you guys understood that continuous does not mean go on forever. Continuous means connected. So when we look at the word discontinuous, that means not connected. But it also doesn't mean discrete. Discrete means just dots. Discontinuous just means that there's, at some point, a break in the connection. So very simply, if I want to say what discontinuous means or show you that, I could draw something that's continuous, and then I have to pick up my pencil, and I keep drawing it. There is a discontinuity there in that function. There's a break, okay? And so often the easiest way to think about what discontinuous means is that in order to draw the graph, we have to pick up our pencil, okay? That the graph can't be drawn without picking up your pencil. You draw one part, you have to pick up your pencil and move it, and then you have to draw the other part. So the graph can't be drawn without picking up your pencil. Because that's how you would create the gap, the lack of continuity, that gap. Okay? So that's what discontinuous means. Or good working definition. So I'm going to quickly sketch for you guys what this function looks like, and then we're going to really dive deep into it, which you see that big table down there and that graph there. There's actually 2 big tables there. We're going to dive really deep into it, the numbers, to see why it's doing what it's doing. But first thing I want to do is just quickly sketch this graph for you. There's the parent function for this family, 1 over x. That's the simplest of all the rational functions, the most basic of them, and 1 over x. And so what that ends up looking like, because we can't plug in a certain number, what number are we not allowed to plug in for x? 0, right? We can't plug 0 in. There's no value for the problem when I plug 0 in. What that creates is something you guys are familiar with now, is an asymptote. At x equals 0, there's an asymptote, a vertical asymptote. Okay? So we're not allowed to plug 0 in. So at that point, there is no value for that graph. Right? There's no value for that graph. There's no value for that function. The other thing that happens is, if we think about plugging in every number but 0, so I plug in 1, I plug in 2, I plug in 3, I plug in 30, I plug in a billion, okay? No matter what, I'm never going to get 0 as an answer. 1 divided by any number is never 0. And so what that creates is a horizontal asymptote, because the y values can never be 0 either. So we've talked about with our exponential functions, they had horizontal asymptotes. We talked about with our logarithmic functions that they had vertical asymptotes. Well, here we're seeing that rational functions can have a horizontal and a vertical asymptote at the same time. Right? Again, this one's just going to be a sketch. We're going to really get into the numbers here in a second. So what we end up seeing, what the graph looks like, is it up here towards the top, on that right side, it's going to scoot along that asymptote just like we're going to used to. Then it's going to curve away, and then it's going to go towards the other asymptote. Okay. You're like, Mr. Baker, I could drew that whole graph without picking up my pencil, because there's more to that graph. It also happens on the left side, but below the x-axis, and then I draw off towards the y-axis, curve, 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 and then scoot along the y-axis going down. So this is what that function looks like. Now what this is called is a hyperbola. So we talked about parabolas. Hyperbola. Okay, so we've talked about parabolas, of course. This is a hyperbola. You may have heard of saying things are hyperbolic. Okay, you can say to somebody that they're being hyperbolic. You can describe a shape as hyperbolic. Okay? So when we're talking about a hyperbolic curve, that might be applied to something that we would want to bend light or bend sound. We might use a hyperbolic dish or a hyperbolic lens to do that, to bend things, to make them change direction. So that is a hyperbola. Okay? So what we're going to do here, again, is just really dive into the numbers here. I want you guys to understand why there's asymptotes and why the curves act like the way they do. And then I'll really pull that back. You guys won't be graphing near this much on anything else that we do, but I just want you guys to really kind of understand this. This is a different type of function, right? That the variable in the denominator just changes the whole way that this acts. So from anything else we've talked about. So just want to look at it. So yeah, we're still just looking at this one, right? The parent function. And I already asked you guys this, and Mason said it was, what number are we not allowed to use as x is 0. And so what that means is that x, can't be 0, right? And this is how we say that x is not allowed to be 0. X cannot equal 0. And what that creates is that vertical asymptote. So this is a little weird, right? We're saying that x can't be 0 here, right? Then we go over here and say x is 0. But what we're trying to do is describe for ourselves this line right here. This vertical line is x equals 0. But we just know that the graph is not going to touch that line, right? We saw up here, right? The graph just kind of scoots along it. But we want to know what that line is. And when we draw asymptotes, guys, those are purely for our eyes. They're not there in the actual graph. We draw them so we can see them, so that our eyes can understand better what's happening. So it's purely a visual thing. It's not actually part of the numbers. It's purely a visual thing. If you notice the x values that I'm trying to have you guys plug in over here, notice that I never don't use 0. The numbers start really big, and then they get really, really close to 0, but we don't reach 0. Okay. And in the same way, like I said before, that no matter what I plugged in, if I plug in a billion up here, 1 divided by a billion is incredibly small, but it's not 0. So there's no number I could ever plug in to make that 0 here. The y values can never be 0 either. So again, there's also a horizontal asymptote at y equals 0. So we're not allowed to plug 0 in, and we'll never get 0 out. That's what that means. Okay. Let's do some arithmetic here, right? So 1 divided by negative 1,000, right? So 1 divided by negative 1,000 shouldn't be too surprising. It's negative 1,000th. Go figure, right? That's what negative 1,000. That's what 1,000th is, right? And then 1 divided by negative 100. It's negative 100. Right? Kind of seeing the pattern how that's going to work. It's negative 0. No, I'll use red for this one. So negative 0.001. So it's negative 0.01. 1 divided by 10 is 1/10, so negative 1/10, so 0.1. 1 divided by 5 is 0.2. That'd be negative 0.2. Whereas 1 divided by negative 1 is negative 1. 1 divided by a half. How many halves are in 1? 2. Right? So 1 divided by half is 2. And so it'd be negative 2. Right? So it's 2 halves in 1. So 1 divided by a half is 2. Well, 1 divided by a tenth. How many tenths are in a 1? Well, there's 10 tenths. Right? And the same way, there'd be 100 100ths to get 1. So that's going to be negative 100. And then 1,000 1,000ths to get 1. That's negative 1,000. So what do we need to see here, right? What's important about this? Why am I having you guys do this over and over again, these numbers? To see that when we plug in these really large negative numbers, we get out these really small negative numbers because we're dividing. So if I divide by a big number, I get a small answer. But when I divide by a small answer, we divide by a small number, we get a big answer. That's how division works. Divided by small things, you get big answers. So as we're really far away from the y-axis, as we're really far off to the left, we get these tiny, tiny numbers. As we get closer and closer to the y-axis, those y values start to change really quickly. Right? Between 1 and 0, it's going, you're not even reaching 0. Between 1 and 0.1, it's already shot down 10. Right? That's a really fast change. So as we get closer and closer to that y-axis, it's going to shoot down really fast. Okay? And of course, we can't plot all of those. I'm just going to look at these 5 here that I can actually plot. Okay? So out here at negative 10, we should be putting at negative 0.1, which is just right underneath the x-axis. Okay, but just give yourself some space because it's not actually supposed to touch, but just put it really close. And negative 5 was negative 0.2, again, just really close, just right below that x-axis. Negative 1, negative 1. Then we said negative half was negative 2, so that should be right here. There's negative half, negative 2, right there. And then at negative 0.1, we should be at 10, which is right next to that y-axis down there at the bottom. Again, just leave a little bit of space there. Okay? Because the graph isn't supposed to touch the line, but limits of pencils and our eyes and all that stuff, it would really be much closer than we could see. So how do I draw this, right? So flat along that asymptote. So really, for most of that horizontal part, it's just kind of run parallel to that asymptote. And then about here, it starts to curve away. As it starts to curve away, it gets close to the other asymptote. So then it starts just running kind of flat along that other asymptote. Arrows on both ends. Okay. We won't normally draw the full curve here because it's kind of a pain in the butt. Okay. But just trying to, again, give you a really good picture of what's happening here with this parent function of this new type of functions that we're doing. So there's one, often called branches. That's one branch of the hyperbola. Well, you can see the numbers I'm asking you guys to use on the other table. It should just be pretty obvious that all those signs are just going to flip. Divide by 1,000, divide by 100, divide by 10, divide by 5, divide by 1. And again, a half gives me 2. What am I doing this here? Tenth gives me 10, 100th gives me 100, 1,000th gives me 1,000. exact same numbers, just no negatives, right? So as we plug in positive numbers, we get positive answers. Again, the very large positive inputs give us very small positive outputs. Very small positive inputs give us very large positive outputs. Again, I'm just going to plot those 5 points that I actually can plot. So way on the right side at 10, but just above that x-axis, there's our 0.1. And then at 5, 0.2. So again, really no difference as far as our eyes can tell. It's really close to the y-axis. Is there hot sauce in there? Is there hot sauce in there?
Yes. Sorry for the interruption.
You're all right. Is there actually hot sauce in there?
Yeah.
Okay.
Somebody try it.
And there's a half, 2, and then 0.110, right? So way up there, just right up next to that y-axis again. So really just going to be drawing that same shape, but just in the first quadrant rather than the third quadrant. Right? It's just a rotation, essentially. Real flat on that y-axis, curve away. Arrows on both ends. Should look something like that. So there's our parent function. Again, really what I want you guys to see is that, why does it curve so sharply? Because we make that division, right? That really small division makes numbers grow rapidly. Right? So in this little tiny space, we have so much y change. Whereas in all this space over here, from like 1 to there's barely any y change here. So that flat space, why is it so flat here? Why is it moving so quickly here? Why is it so steep here? Why is it so flat here? Right? Just trying to understand that. All right, so here's our our essential question: domain range. Hey, Kim. There's a few papers right here. Right. Well, domain and range. I mean, it's still domain and range. Can't change that, right? Just something to be a little bit different about it. So domain is our x's, and so we always think left to right. Right? So we look at that left end of the graph, and there's our negative infinity arrow, right? It's going left forever. Nothing new about that. Well, as we go to the right, we're following along, and the graph's like, I really don't want to touch 0, right? It's like, okay, well, don't touch 0 then. Well, we've seen that before. Okay, so we're going to get really close to 0, but we're never going to touch it. So that's what the parenthesis says. Just get just shy of 0. But what's different here is that we do have that other branch, that discontinuity. We've never had that before. More graph after the graph is like, no, I don't want to do that. Well, as soon as we flip to the other side of 0, there's the graph again. Just on the other side of 0, though. Right now it's on the positive side of 0. And then it goes, well, I'm good to go the rest of the way. So how do we do that, right? Well, we just start writing again. Just on the other side of 0, and then to the right forever. Okay? So we have 2 intervals for our domain. We've never had that before. And the way we join those is with what's called a union, and that's just a U, a big old capital U. So that stands for the word union. Really what you guys need to be worried about with the word union, or what union means, is just or. Okay? Domain is about the inputs. What numbers can we put in? This is saying we can plug in numbers that are less than 0. Or I could plug in numbers that are greater than 0. There's an implication there. If I can plug in numbers that are less than 0, or I can plug in numbers that are greater than 0, I'm implying I can't plug in 0. Okay? So within the domain, there's the implication of this. Right? Hey, what can't we do? That's what this is saying. Okay? I can do less than 0. I can do more than 0. Well, I must not be able to do 0. Okay? That's what it's saying. Well, what's the range all about? Range is up and down, but remember, you always go low to high. So I start on the low end. What do I see down there? Well, there's that down arrow. I know how to do down arrows. That's negative infinity. And as we move up the graph, it's like, I really don't want to touch 0. Right? So it doesn't. So it just stops just short of 0. So we know how to deal with that. That's parenthesis. Again, the weird part, there's more graph. So just on the other side of 0, starts to go up again, and it's all good to go forever. So the domain and the range actually look exactly the same. So negative infinity to 0, union 0 to infinity. But they do mean different things, right? What x's can I plug in? What are the answers that are going to come out? So we're going to get numbers that are less than 0. We're going to get numbers that are more than 0. But we're not going to get 0, right? Which we said here. That graph is never going to equal 0. That's why there's an asymptote there. So this is how we do domain and range for rational functions. They have 2 intervals for both. That's definitely new for us. Okay. But if we go back to how we've always found domain and range, we should be able to do that. Any questions there before we get into these little functions down here? I want to talk to you guys about the shifts and stuff. We won't be doing any reflection stretching today. We'll do that Monday. Today we're going to talk about our shifts, which we've talked about shifting multiple times. It shouldn't be again anything new, but just a new shape of the graph. Is there anything you guys want to talk about first? Oh, and this very last one here should be a plus. I copied it and I forgot to change it, so that needs to be a plus. Oopsie poopsie. Right? So we've seen all this over and over again, like, where the number is just as important as what the number is, and what its sign is as far as telling you how it's going to affect the shape of the graph, right? So this is all just transformation stuff. It's our shifts ups, our shifts downs, our shifts lefts, our shifts rights. Okay? That's all this is. Again, we'll do the stretching, reflecting stuff on Monday. Okay? So let's just go ahead and look at this one here. I'm going to go ahead and graph it for you guys. So we just saw the parent function. So how is this function different than the parent function? You guys see? It's been what? Shifted right. Okay. So we see 1 over x minus 3. Right, there's that minus 3, but it went right. So there's our liar, right? That's shouldn't be a new thought. That's the one that's going to lie to us down there. Okay. What I really want you guys to focus on here is actually the asymptotes. So that minus 3 is going to affect that vertical asymptote. It's going to push it to 3. So it was at 0, now it's at 3, because that was a shift right 3. And we just talked about this with the logarithmic graphs, how that right shift or that left shift can affect that vertical line, can make it move side to side. Now, a right shift is not going to affect the horizontal line. Our horizontal asymptote doesn't change from y equals 0. This is the part I really want you guys to focus on for these things. And then we'll just sketch in the graph. Like, well, what's a rational function look like? What's a hyperbola look like? Looks kind of like that. Yeah. The main thing I really want you guys to get from here is how does that shift affect the asymptotes? We see how it's affecting that guy right there. Okay. So that's what 1 over x minus 3 looks like. These are just purely sketches. I just want you guys to kind of get an idea in your head what this is going to do, right? That's all this is, just getting ideas. Yeah. So what's the plus 3 going to do?
We're technically going to push around the origin.
Yeah, right on. Mason just said we're kind of moving around the origin, right? Because if you think about where those asymptotes were originally intersecting was the origin, right? So now we're just taking that intersection and moving it away from the origin somehow. So yeah, good observation, Mason. So, right, plus 3, see the graph went left, right? So again, there's that liar. So, what do we want to highlight for ourselves here? Plus 3, that's actually left shift. So that's going to take my asymptote and move it to the left. Instead of being at 0, it's going to be at negative 3. And there's nothing special about 3. I just picked a number. Like, it could have been 5, it could have been 1. It's decided to use 3. But that left shift does not affect our horizontal asymptote. And I'm just going to sketch in what hyperbolas generally look like. like they do that. They look like they do that. That big thing in, left shift, affected the vertical asymptote. Okay. So, what I've always talked to you guys about is like, the left and right shifts are inside the function, right? Well, how do we identify the inside of a fraction? Well, if you think about where that 3 is, in either case, whether it's positive or negative, it's in the fraction, right? It's in the denominator. That's where the variable is. It's in the denominator. So if the number is also in the denominator, then it's on the inside, okay? Versus being on the outside or after the function, right? Look where the 3's are now. They're not in the denominator, right? They're after. Just like always with the after stuff, those are our up and downs. And with the up and down ones, we've always been able to trust them. Okay, so we know that our left and rights are our liars. Our up and downs, we usually are pretty good with them, right? And we just confirm that yep, 1 over x minus 3 did indeed shift it down. Okay. So what's changing here from this minus 3 is the horizontal asymptote. So I'm going to take that horizontal asymptote, I'm going to shift it down -3, or to -3. My vertical asymptote is going to stay on 0. So here's the change we really want to pay attention to. Right, what changed? And then again, I'm just going to kind of sketch in what a hyperbola looks like. It scoots along one asymptote, curves towards the other asymptote. Looks like that. It is a curve. It's not an angle. Scoots along one asymptote, curves towards the other one. Okay. So it should kind of be nestled in there where they intersect. Okay, they shouldn't be way apart. Okay. So of course that was down 3. And we shouldn't even need to look at the last one to know what it's going to do. All right, that +3, make sure you change that. It's our up 3. So that's going to take that horizontal asymptote and shift it up to y equals 3. And our VA, our vertical asymptote, not going to move. You will hear me start saying VA or HA or writing VA and HA. This is just not always fun to have to say vertical and horizontal asymptote over and over again. So just be aware of that. VA, vertical asymptote, HA, horizontal asymptote. I was a little bit afraid when I have to say the word asymptote over and over again throughout the day. And that was purely just sketching, guys, trying to get an idea, see how things are going to move. But hopefully it's nothing too surprising there, because we've talked about transformations so many times. Just kind of have a pretty good feel for that. But here on this next problem, we're actually gonna I'll show you how to do it. That is hideous. What the heck? Wow, no. My wife just sent me a picture of a rug. I don't know if she's being serious about buying it. No, I need to quickly respond. No. Nope. 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 No. There. Okay. Sorry. Anything here you guys want to talk about before we actually kind of get into how we're actually going to do the graphing? Everything else right now has been so far just kind of an exploration. This is actually the way I'm going to want you guys to do things. June, you good? Jubal? Sophia? Silent masses? Oh, it's fine. Who knows? You guys get what's going on. You're important. Okay. All right. So we're going to find the asymptotes. I put that at the front for a reason. I really do think that's the most important thing you guys need to focus on is finding the asymptotes. Sketch the graph and do domain and range. Okay. I really do think what I'm about to show you guys is the easiest way to go about doing what we're about to do. Okay. So I'm being very deliberate in what I'm asking you guys to do, the order I'm telling you guys to do it in, and all that. It's all for a reason. So we want to start by setting up the asymptotes because they really are going to be our guides to everything else that happens in the problem. Okay? And to prompt our brains to say, well, where are my asymptotes? it's thinking about this question. What value of x can't we use? We saw earlier that when we couldn't use 0, that directly linked to that vertical asymptote being at 0. So we look at this denominator and say, what value can't x be? 2, right? 10. So if x can't be 2, then that means we have, I should not write it right there. X can't be 2, that means we have at 2 a vertical asymptote. So very directly from that thought of x can't be 2 means that x equals 2 is a vertical asymptote. Not allowed to plug in 2 because it makes the denominator 0. So we're going to draw this line here. And again, anytime that the asymptotes are shifted off the axes, I do want you guys to draw them. The whole point of drawing an asymptote is so that you can see it. If you don't draw it, you can't see it, and it doesn't help you at all. Okay? They're not mathematically there. It's really just a purely visual thing that we do for helping us graph. So there's our vertical asymptote. We also need our horizontal asymptote, and we know it's supposed to be at 0, but we have that. Right? So there's our right shift. Well, here's our up shift. Oops. So at y equals 3, we're going to draw our horizontal asymptote. Okay. Yeah, I do think doing those two things is going to be the most important thing you guys do for as far as these graphs. So anything you guys need clarity on how we've got those two lines? They should always be dashed lines. So if we're going to generate a graph, we need to have points. In order to generate points, we need to pick x's. So I don't want you guys picking x's randomly. What I want to show you guys is a pattern that I've just kind of developed over doing this over and over again that's just kind of useful. There's nothing magical about this. You may go learn this from somebody else and they would never say anything like this. It's purely just something I find useful. Okay? So there's 7 boxes there. You guys are going to need to find 6 points, okay? Because we are doing 2 graphs, essentially, 2 separate graphs. We're going to do 3 for each. There's 7 boxes. Why, you ask? Because of this. Right? That's the center of the graph. Right? The new center is here, right, as far as x values. We need to graph on the right side of that. We need to graph on the left side of that. So we need to be looking at that number we know is not going to work. That's the first number we're going to put in our table right there in the middle. And we know it's not going to give us an answer. But why are we doing that, right? Just so we can focus on, here's the middle of the graph. I want to go on both sides of that. Okay? So we're going to graph on the right side of 2. We're going to graph on the left side of 2. Again, I'm going to tell you guys a pattern to use. Purely my thing. I just think it's a good thing to do, because what happens here, when you graph these guys, this is where all the action is. Right up next to that asymptote. We kind of know what's going to happen here. It's just going to go pretty much straight up. We kind of know what's going to happen out here. It's going to pretty much go straight to the side. We need to make sure we graph this curve here correctly. That's where it's happening. So what I ask you guys to do is to go half away, 1 away, 4 away. Okay? So I'm going to go a half to the right of 2. So 2.5. I'm going to plug that in. I'm going to go 1 to the right of 2. 1 more than 2. 3. I'm going to go 4 more than 2. Half away, 1 away, 4 away. On the left and on the right. So there's the right. Right? I also want to do that on the left. So a half less than 2. So 1.5. 1 less than 2. 1. 4 less than 2. Negative 2. So a half away, 1 away, 4 away in both directions. So these two here, guys, are the action. Here's where the curving is going to happen. And then this kind of just lets you know what's happening as you move off away from things, right? Just to kind of give you a guide. Okay, so these are the action points. This is the one to kind of say, okay, here's where it ends up going. action points, here's what it ends up. That's the only reason I'm doing this. We need to be up close to that asymptote, and we just kind of have an idea where we're headed. Okay. Well, now we need to generate all those y values. I don't want you guys to burn yourselves out doing a bunch of calculations by hand. Certainly not. And I don't want you to burn yourselves out and do a bunch of calculations in your calculator. So I'm going to show you a faster way to use your calculator to do this. Okay? But we need to start with our calculator. So again, you do need a decent calculator to do this, one that has parentheses on it. So whether you're using your app or you're using your TI, whatever, get that out. But we got to start somewhere. So I'm just going to start with this top one here in the purple. So 1 divided by 2.5 minus 2 plus 3, right? That's what we should type in our calculator. Fractions and calculators don't talk very well together unless you're very specific to them. Hey, buddy, this stuff here is in the denominator. Pay attention, okay? So you've got to get those numbers there in parentheses. If you don't put them in parentheses, you're going to get the wrong answer, okay? So 1 divided by, parentheses, 2.5 minus 2, close those parentheses, and then plus 3. So 1 divided by parentheses, 2.5 minus 2, close the parentheses, not open the parentheses, close the parentheses, plus 3. Okay, so we get our answer, right? We plug in 2.5, it spits out 5 for us. Well, we have to do that 5 more times, right? So how do we do it faster? So if you're using this app, or most apps, all I have to do is go and tap that thing that's up there in the top left, the thing I typed, and it brings it back to me, and I can just go and change that one number. Right? Now I want it to be 3 instead of 2.5. So I make sure I hit delete, not clear, and I change that to a 3, and then I hit enter, and it does the math for me. So I hit tap it, and I can go and edit it. I want it to be 6 next time, so I change it. Now I've done those 3 calculations quickly. If you're doing it like a smaller TI calculator, okay, TI 30, works just fine. I turn it on first. So you type it in, you get your first answer, and then you just hit up. And it takes you back to the last thing you typed, and then you can go and edit it. So if I want to change that 3 to a 6, I can do that very easily. It is kind of difficult on the TIs to make the number longer. Like if I want to change a 3 to a 6, that's easy. But if I want to change the 3 to a 3.5, it's kind of a pain. There is a way to do it, but it's kind of a pain. Probably easier if I could show you like in person, just stuff. But there is a way to do it. Or if you really want to spend time about it one time. But you just hit up, and then you can go and change it. And you can quickly do it. TI 84s, TI 83s, pretty much the same thing. Type it in one time, okay? Hit enter, get your answer. And then what you're going to do is you hit second enter. Let's see, it says entry. So second enter, and it'll bring back up the last thing you typed, and then you can go and edit it. Again, don't hit clear if you're trying to get rid of something. Hit delete. But most of the time you would just replace the number. These things, TI uses an overwrite function. So if you want to take a 3 and turn it into a 6, you just go to the 3 and you type 6 and it overwrites it. Don't delete it and then try to replace it because that screws it up. But some of that stuff you guys have to learn by practicing. Okay? So we can do those calculations more quickly. I don't want you guys typing it. It's going to burn you out. Okay? That was 3, 5, 4. So it's good just to know some of those tricks. 2, 5. So then we need to do the left side. So I want to go to 1.5. And then I want
6 minus 2.
See?
1 over 6 minus 2.
Oh, I said 4 away, and then I wrote 4. I said the right thing, and then I confused myself. All right, 4 away from 2 is 6, not 4. Thank you for noticing that, Mason. Yeah, Mason noticed that I said 4, then I wrote 4, instead of adding 4 to 2 and getting 6. Yeah. Nope, I don't want 3, I want 1. And that could be -2. So I got 1, 2, 2.75. 1, 2, 2.75. So there's my points I want to plot. So 2.55, well, there's 2.55 is right there, 2.55. And then 3, 4, 3, 4, there. And then 6, 3.25, so 6, 3.25 should be right above that asymptote, right? It should be getting close to the asymptote at that point. So shouldn't be surprising that we're getting really close right at the 3.25 is right there. I'll zoom in a little bit. I like to go ahead, once I have those 3 points drawn or plotted, I like to go ahead and draw that part of the graph. But if you want to do all 6 and then draw the graph, what you can. But right along that vertical asymptote, curving, here's those action points where the curving is happening. And then that 4 away point lets you know where things are headed off to the right. Okay? So half away, 1 away, 4 away is the pattern I'm recommending. And nothing magical there, nothing required there. I just think it's a good pattern to see. So 1.5, 1, 1.5 is right here, 1 right there. 1, 2, and then -2, 2.75, so -2, 2.75 should be right below the asymptote. There's 3, so right below it. So there's the other branch of the hyperbola plotted. And that vertical asymptote, just kind of scoot along it. Curve through those action points, curve towards that -2 one. And just go along the asymptote just a little bit. You guys certainly do not need to go all the way to the left, just a little bit. Yeah, what you should not be doing there as you head left or head right is, you should definitely not be crossing the asymptote. That's definitely a no-no. And you shouldn't be belling down or up. Shouldn't be curving away either. Right? Math tells us that line is supposed to keep getting closer and closer and closer and closer and closer. But we can't do that. You just kind of draw it running next to it. So that's what that graph should look like. So domain and range. Oh, I did that. So domain, left side, there's our arrow. It's like, I'm getting really close to 2. I don't like that. So left infinity to 2. So negative, come on, negative infinity to 2. Close that parenthesis. We use our union symbol because on the other side of 2, it starts going again, heads off to the right forever. But it shouldn't be surprising that we just wrote 2 there because we've seen 2 so many other times already. I mean, here's that 2 here, here's the 2 here, here's the 2 here, here's the 2 here, here's the 2's again. All of those 2's are the same 2. They're all connected. Okay? So it shouldn't be a mystery what's going on with the domain there, right? Like the domain, 2 is the number we can't use. We knew that a long time ago. Okay? And with the range, starts off pointing down forever, gets like, I really don't want to get to 3. So it curves away. Just short of 3, but then on the other side of 3, union, it starts curving up again. Again, that 3 shouldn't be a mystery because there's the 3, there's the 3, there's the 3 again. Okay? That we're not allowed to get 3. That's what that means. We can get everything below 3, we can get everything above 3, but no 3. Okay? All right, I know we're getting close on time. We got 5 minutes, so may not be able to finish, this next example, but definitely getting it set up, and so you guys can make sure you understand how to do that. So, and I'll finish it, make sure it's on the video, but just the setup part of it, at least. Okay? How do you get your table set up and getting those asymptotes down and stuff like that is really the key to it. So. What I want to look at first when I starting this thinking, I always look at the denominator and say, hey, what can't x be? Or I should be saying, hey, what's my transformation there? What value of x can't I plug in? because it's going to make it 0. So -4 plus 4 would be 0. So x can't be -4, which means at -4, we have our vertical asymptote. So you can just watch that because here we're saying x can't be 4, then right below that I'm saying x is 4. I totally get that that could be confusing. And this is an equation of a line, so that's why we're saying here. But we're just making note to ourselves that nope. And as soon as we know that, we can also say, oh, that means that -4 is going to be the middle of my table. So just by looking at that one spot, I know my vertical asymptote, and I know where my table is going to start, or it's going to branch out. Okay. But before I go and worry about the table, I'm going to finish up worrying about my asymptotes. So I always look to see what's after the function. So there's a -1, so that's going to give me my horizontal asymptote. So down here at -1, draw that dashed line. Anything finding asymptotes you guys worry about? We know our middle value of our table. We want things on the left and the right of -4. Again, the pattern half away. So if I go half to the right of -4, that gives me to -3.5. 1 to the right of -4 is -3, and 4 to the right of -4 is 0. There's going to be the right side, and half to the left of -4, -4.5, 1 to the left of -4, -5, and 4 to the left would be -8. So those are my x values. We'll just plug them in, figure out our y values. Okay. You guys should be able to do that on your own, and the graph's going to end up looking like something like that. Okay. I think the domain and the range are a little bit more important to talk about than say you're running a bunch of calculations. Domain is about those x values. Really, if you guys just identify that in that one x value that we can't use, that's the one that you really, is highlighted here. It's always going to be -infinity to something. We said no to -4, so there's our stopping. Jump over -4 and keep going. Okay, so there's that. I don't know why I wrote 4 up here. That should be a -4. Just notice that. That should be -4. So we said no to -4. There it is again, right? There's -4, -4, -4. And then the y value that we're never going to get is that -1. So -infinity to -1, union -1 to infinity. I'll pause this now, and I'll go through and I'll do the calculations and show you to do some calculations here. Need to plug those x values into my function here. So I'm going to do 1 over, let's start with 1 over -3.5 plus 4 minus 1. So again, key there is going to be the parentheses that we're going to put around the denominator. So 1 divided by parenthesis -3.5 plus 4, close those parentheses, and then minus 1. And then I want to quickly go and do the other calculation, so I'm going to just tap that, and I'm going to edit it so it's -3. And then the other x value we were going to plug in on the right side was 0, so I'm going to turn this into a 0. So 1, 0, -7, -0.75. 1, 0, -0.75. All right, then I'm going to go ahead and plot those. That's the way I usually like to do this. So -3.5 here, 1. So -3.5, 1 here. -3, 0. It's easy enough to find. And then 0, -7.5. So 0, and -7.5. And I didn't do a great job of writing this. Clean that up a little bit. Asymptote. So 0, -7.75 is right here, right above that asymptote. So how do I draw that? So on that left side, just kind of scooting along that vertical asymptote, just kind of parallel to it. Curve through those action points there. as it heads off to the right, it's just going to get kind of flat, head towards that asymptote. Again, just really don't want you to bail out, or definitely don't want you to cross town. So that's the right side. Now I need to do the calculations for the left side. So I want this to be a 4, so we'll change that. And then I wanted -5. And then I wanted -8. So -3, -2, -1.25. -3, -2, -1.25. So -4.5, -3 would be right here. -5, -2 is right there, and then -8, -1.25. So that should be just below that line. So again, it's kind of sloppy with the way I drew my asymptote, so I'm just going to clean that up a little bit. -8, -1.25, just below that line. And flat along that vertical asymptote. Oops. Curve through those two and head towards that left point. Oops. All right, so there's that other branch of the hyperbola. Let's see it. So I guess while I'm here, I'll go ahead and do that one. So I want to start with the vertical asymptote. So what I'm going to do is look for a value of x that I can't use, which would be 0. X cannot be 0. Can't plug 0 in there. So x cannot be 0, which means that x equals 0 is my VA. And then that means that 0 is going to be my middle value here in my table. And then what about that horizontal asymptote? So I'm looking at the shift up here. So that's a 2, so that's going to be a y equals 2. There's that. Real estate, with the information I have right now, I can go ahead and do the domain range. So the x values are going to start all the way to the left, keep going until they head towards that asymptote, which is at 0. And then on the other side of 0, they're going to start going again. And we're just going to join that with the union. And pretty similar thing with the range. It's going to start down forever. And then it's going to head towards the asymptote, which is at 2. And it's going to jump to the other side of the horizontal asymptote at 2 and keep going up forever. So use that information right there. Let's get some points. So I want to go half away. So 1/2 more, 1 more, and 4 more. I'm going to go a half below, so -0.5, -1, and -4. So half away, 1 away, 4 away. It's my pattern I like to use. And purely just something I like to do. So my function was 1 divided by x, so x was 0.5. Now, I don't need parentheses here because it's just one number. It's not like 0.5 minus something. So technically, I don't need parentheses. And if I want to be safe, I can always put them in and just get that habit. Habits are good for this. And then +2, right? So, oops, I forgot to hit 2. Calculator's like, what are you talking about? All right, +2. Then we wanted 1 away, so I would change that to a 1. And then I wanted 4 away, so I'll change that to a 4. So 4, 3, 2.25. 4, 3, 2.25. So 0.54. So a half 4 is right here. And 3, and 4, 2.25, just right above that asymptote there. And scoot along that vertical asymptote, just kind of flat along it, curve through those 2 points here towards that one on the right. Make sure you're drawing a curve, not an angle. And then I'm going to do the math on the other side, so if I make those negative, so negative 0.5, negative 1, and negative 4. Got 0, 1, and 1.75. 0, 1, and 1.7. So negative half, 0, should be right here. Negative 1, 1. And negative 4, 1.75. Right there. So I just need to finish drawing this curve. So flat along the asymptotes. And down on that one. All right. Should be all you guys need there on all those. Enjoy.